It is our University of Calgary team first time participating in the Drillbotics competition. Our design was determined based on the guideline and lessons other teams have learned. During the first several weeks, strengths and weaknesses of the previous year's models were discussed and analyzed. The final design incorporates the idea of counterweighting to recreate the weight on bit as desired. Furthermore, this method is expected to reduce the power requirement from drawworks. The pneumatic actuator is employed to balance the drilling tower because of its versatility and accuracy. This actuator is selected due to its high precision resolution and therefore can provide precise directional steering. The sensor system is developed based on the actuator drilling rig, the actual drilling rig. However, minor details are added to observe our objective functions: smooth vertical hold condition and speed of penetration. To this end, this design is expected to initiate the new drilling rig idea and achieve the competition goals. The safety system is integrated with the control system and sensor scheme. Since this competition is our first experience, our conceptual idea is founded based on the lessons learned from the previous models. As stated in the previous section, the drilling tower is the most critical part. The tipping failure may happen when the system tries to balance the WOB regarding the control system identify. Therefore, in the case of the potentially tripping happen, the overall operation is ceased. Subsequently, activate the alarm. Spring systems also help to balance the tower and are placed between the tower and table around ball joint connections. In the drill bit, BHA, or drill pipe stuck situation, the sensors that are located in the drill string signal the control system to stop the top drive to prevent the pipe breakdown. For the mud system, if the rapid pressure drop occurs, subsequently meet the threshold value, the sensors will alarm and stop the mud pump.
The drilling tower is an essential part of our drill rig. In order to support the 220-pound tower and provide strength to the structure, several 80-20 aluminum beams will be used. What makes this drill rig outstanding from previous designs is its capability of steering, tackling any inclined formations we might face while drilling, and preventing any damage to the thin drill pipe. This will be made possible by using 2 pneumatic pistons, 3 ball joints, and the stabilizer on the bottom hole assembly as a pivot point. One piston will provide forward steering and the other will provide side steering. Combined with the vertical movement provided by the drawworks, the drill bit will have a 3-axis maneuver. The degree of steering will depend on the positioning input given by the gyroscope sensor placed in the BHA, allowing the drill bit to drill perpendicular through any formation.
The drilling rig is going to need various sensors to collect data so that we can assess the current state of drilling. Integrated into the top drive, we will have sensors for 3 main important parameters. The first parameter we will be looking to measure is the RPM and torque. This will be done using a variable frequency drive as well as a torque sensor. The second parameter we will be looking to find is the position of the top drive. Since we have a pneumatic system to adjust the angle of drilling, we will be using gyroscopes to find the angle of the top drive. And to find the vertical position of the top drive, we will be using an optical sensor which can measure how many units up or down the top drive has traveled. The final parameter to be measured in the top drive is vibration and resonance. This will be done by installing a triaxial accelerometer onto our top drive. The next place we will need to place a sensor is along the drill bit itself. This will be used to measure the weight on bit. To do so, we will employ an S-beam load cell between the drive chain and top drive motor. The mud system will also require 2 sensors to ensure that it is functioning properly. These sensors include both a flow meter and a temperature probe. The bottom hole assembly, like the top drive, will require us to use a set of various sensors. In order to find values such as inclination and azimuth, we will be using a magnetometer and a gyroscope. We will also be measuring the downhole vibration by using an accelerometer, And since these sensors are not easily accessible as those on the surface, we'll be using a Bluetooth transmitter to send back data collected. In order to actually see the data, we will be using an analog to digital converter, which will convert necessary measurements over so that they can be used by our Raspberry Pi unit. This Raspberry Pi unit will then transmit the data over to a computer, which will display all of our collected information in a LabVIEW program.
The information from the sensors will first be processed by the respective controllers before being sent to the computer for viewing. The control system will then process the information from the sensors to optimize drilling performance, and the software will also stop the system if something unexpected happens. This maintains safe drilling and prevents damage to the rig. The controllers will then communicate with the hardware interface, such as the VFD or the pneumatics controller, to control the various equipment on the drilling rig. The rig will be made mobile by the addition of wheels under every table leg. These wheels could be locked during drilling to prevent the rig from moving around and could be unlocked when the rig requires moving. The tower can also be tilted up and down. This allows for room so it could clear doorways without hitting the top.